proud of Nick's progress and trajectory and the time that he's been here. Came here with this great idea for a project. Many students come here and wait to be given a project, and Nick actually had this inkling of an idea about being interested in self-lensing black hole binaries.
From a conversation with you down the hall 5 years ago, actually.
So I just basically encouraged Nick, and various people in this room have encouraged Nick as well, and we've been very happy with your work. You published, I think, 3 papers, first author papers. Won this great grant from NASA, which is a great achievement for graduate students for any institutions to achieve. Things are pretty competitive, and we're very proud to see you going off into the world. You've already been hired into your first job, and you haven't even defended your PhD thesis. So, this is great progress. So, congratulations on that so far. And we hope that your talk today doesn't do anything to change your opinion of that. So, with that, I'll get out of the way and let Nick tell us all about what you've been doing in the last.
Thank you for those words of encouragement. So thank you all for joining me here today. We have a great collection of friends, family, colleagues, obviously our very distinguished committee members up in the front, Professor Silas Laycock, my advisor, Professor Offer Cohen, and Professor Nishant Agarwal. As Professor Laycock said, I'd like to welcome our 4th committee member who's joining us online via Zoom, Dr. Tansu Dalen. Tansu earned his PhD at Harvard, did postdoctoral research work at both MIT and Princeton, and is currently a professor of physics at Washington University in St. Louis. So I really appreciate him joining us here today. With all of that out of the way, I think I'll get started. So I'm going to defend my dissertation titled The Development and Application of SMILE, a Stellar Compact Object Binary System Light Curve Model. And yes, that is basically the longest possible title I could come up with. For those who are a little bit less familiar with the terminology, there's quite a bit in that title. So I want to break down some aspects of it first before we get into what exactly SMILE is. So the first word I'd like to start with, there's a little bit of a delay. There we go. What are light curves? That was part of the title. So light curves are a collection of data that tell us the brightness of a star as a function of time. An example of a light curve can be found right here. We have a graph with a lot of data points on it. You'll notice on the x-axis, we have time in days, and on the y-axis, we have this thing called relative flux. Relative flux is just a measure of how bright a star is relative to its average brightness. So a relative flux value of 1 just means that star is at its average brightness. Now, looking at this particular light curve, you may think that there's a lot happening here. There's a lot of noise, a lot of up and down motion. There's kind of like this spread to the data points. There's a lot of data. And you may be tempted to think that the star is doing a lot. But if I were to draw this red line directly through that relative flux value of 1 through the star's average brightness, you end up finding that that value stays relatively in the middle. And the reason for that is the spread that we see is more or less just statistical noise. Whenever we go out and collect photons with telescopes, there's always going to be some level of noise. So we get a spread like this. But in general, what we can tell from this light curve is that the star actually really isn't doing too much. It's more or less staying the same brightness as function of time, and is in some ways uninteresting. But light curves can be very interesting, and a great example of that would be this one here. You'll notice these very large repeated dips in the star's brightness. The star is getting dimmer from our perspective on Earth. And based on these signals that we see, we actually can learn quite a bit, not only about the star, but what is happening in this system. So each one of these dips corresponds to an exoplanet transit. There is what we call a hot Jupiter in the system. It's a planet that is a lot like our planet in our solar system, Jupiter, about the same size, but it's very close to its star, so it is very hot. Now, just by looking at the light curve, we know all of that information. We know relatively how large the planet is based on how much light is being blocked. Every time the exoplanet passes in front of the star, we're going to see that light get blocked. That's why this is a repeated effect. So every time the exoplanet goes around its star, we get another dip. Likewise, based on the frequency of these dips, we know the orbital period of that planet. If we look at the x-axis, we can see this happens roughly every day and a half, meaning that that planet's year is only a day and a half long. So it is very, very close to its star. So even again, in this one example, we've learned quite a bit about what's happening. We also can learn what kind of stars we're looking at based on light curves. And a good example of that would be this here. Based solely on this shape, we know this is what's called a Cepheid variable star, which change brightness very rapidly and very extremely. These are one of those standard candles of the universe. So light curves in general are very useful, and they are the data set that we primarily focus on with our modeling. So what is SMILE, the next part of our title? So SMILE is an acronym. It stands for Self-Lensing Model Involving Limb-Darkened Ellipsoidals, or as I call it, the only combination of 5 terms even remotely related to this project that gave me an acronym that was relatively marketable. Because as Silas and I found out relatively early on, maybe over the course of the first 3 years of our project, is that there seems to be some kind of interesting direct relationship between the quality of your project's name and grant money. You see, the first 3 years, we didn't really have much of a project name, and we just kind of made it up as we went. And we did not have any grant money. But practically immediately after coming up with the name SMILE, coming up with a cool name, I'm noticing a trend here. Throw on a fun logo you made in a combination of Mathematica and PowerPoint, and all of a sudden that 1 year of business school I did is practically paying for itself. So that's what SMILE stands for. That's why we chose the name. But what is SMILE in the end? So SMILE is a light curve model, meaning it simulates how a star's brightness changes as a function of time under very specific circumstances. So if I have a light curve like so, what SMILE's job to do is to fit to that data, something like this. And based on that fit, we will learn what is happening in this kind of system. So what kind do we care about? Well, the last part of our title. These are stellar compact object binary systems. So in these kinds of systems, what we have is we have a star and some kind of compact object like this black hole that I have in this particular case. It doesn't have to be a black hole. It could be a neutron star. It could be a white dwarf star, just some form. And in these kinds of systems, what's happening is that the objects are orbiting around a shared center of mass. They are gravitationally attracted to one another. Orbit, so it's not perfectly circular. There will be points where the two objects will be closer together, and depending on if they're closer or farther, they'll either be moving faster or slower. And when you have situation effects that are that will be present in the light curve based on how close they are together as a function of they're moving relative to one another. So by modeling these effects that appear in the light curve, we can learn what's happening in the system. We can make parameter estimates. We can estimate the mass of the compact object, the mass of the companion star, the radius of the companion star, orbital inclination, eccentricity, period, amongst a handful of others. For us astrophysicists, these are all very useful things. They give us a much clearer picture as to what is going on in the system. Mass is very important, especially for compact objects. We can learn quite a bit based solely on mass, especially with black holes. So this is something that we want to do. We want to go out and look for this. So what effects are included in SMILE? I'll start there. The first effect is called relativistic Doppler boosting. I have a good example, like a visual aid as to what is more or less happening. This isn't necessarily particularly what we're looking at, but if you have a luminous object that is moving very fast towards you, what will happen is, from our perspective, it will actually appear brighter than if it were staying still. Likewise, if this luminous object is moving very fast away from you, it will appear dimmer. So in this case, I have a black hole that has an accretion disk of very fast-moving hot material that is slowly falling into the black hole. And on the left side, what we can see is that the material is very bright. And on the right side, the material that is moving away from us is very dark. So left is moving towards us, and it's much brighter than the stuff moving away. Now, in our specific case, the thing that is moving, the thing that is luminous and moving towards and away from us is actually the star in our binary system. So I have a star denoted by this orange circle here, and I have it going around a black hole denoted by that black circle. We have a very happy distant observer located on the left, and that's the line of sight that he'll have. And what we'll see is as the moving away from us, it gets dimmer. And as it's brighter. Okay. Or dim, the star will appear. It is tied directly to the radial velocity of the star, so how fast it is moving towards or away from us along our line of sight. So if it's moving faster, we should see a greater change in brightness, and when it's moving slower, we should see a smaller change in brightness. Now, the next effect is ellipsoidal variations, and this is the E in SMILE. So in this case, similar thing, I have a black hole with a star. The black hole has a lot of gravity, and it is pulling very hard on the surface of the star, which can result in the star's shape being deformed. This is a very extreme scenario, or very extreme case of it here, but what we can see is that the star is now this kind of balloon or teardrop shape. And depending on where the two are in their orbit, we'll have different perspectives of the star. So we'll see kind of different shapes. It'll either look almost circular here, but then when it's on its side view, we have that balloon shape. And as the two go around each other like this, what we'll see is that the star will either appear brighter or dimmer, depending on the perspective we have of it. And the cause of that is an effect called gravity darkening. So as the black hole squeezes on the star, it's stretching in one direction and squeezing in the opposite direction. The parts that are being stretched away are being stretched away from the core of the star, which is the part that's heating up everything else. So those parts here and on the other side here are going to be physically cooler and then dimmer from our perspective or in general, whereas the parts that are being squeezed in will be hotter and thus brighter. So if we have this view of the star, it will be brighter. And if we are looking at this blue part here, it will be dimmer. Now, the last major effect that's included in SMILE is our bread and butter. It's the reason that we got started with this. It is called gravitational lensing. And it is a consequence of Einstein's theory of general relativity. So compact objects are very dense and possess so much gravity that they bend the very space in their immediate vicinity, which causes light emitted from sources that are behind them to be deflected in many ways, like a lens, hence the name. So as an example, let's say I have a black hole right here. It's a little dark in here, but you can see it. And what's going to happen is that this black hole is going to pass directly in front of this bright, distant background star. And as it does so, as it starts moving directly in front of it, oh, actually, sorry, this is what's called the Einstein radius. It is a ring that forms around the black hole. This will be important in just a minute. Now, as the black hole passes in front of the star, what we'll see is that the star's shape gets deformed. Its surface area is increasing. Likewise, we also have the formation of a more prominent second image. This is the same star, but we actually see it twice now. And because it's getting bigger, and because we see two of it now, it is getting brighter from our perspective on Earth. As the black hole passes directly in front of the star, in the case of a point source, we'll get the formation of what is called an Einstein ring. Both images, secondary and primary, will kind of combine into one big image. And this Einstein ring forms at the Einstein radius. That's what makes it a very special radius. And at this point, we'll see the peak increase in brightness of the star from our perspective. And then as the black hole starts moving away from the star, it will return back to its original brightness. Now, in our case, the star and the black hole, or the compact object, are in the same system. They're orbiting around each other. And what will happen is if the black hole passes in front of the star from our perspective, so if the inclination is approximately edge on, so I equals 90 degrees, what we'll see is in the light curve is the star will get brighter for a period of time. There will be a kind of flash of light before it returns back to normal. Now, these are very useful because kind of like the exoplanet transits, these immediately constrain the inclination of the system. It has to be practically edge on for this effect to occur. If the black hole does not pass near the star, we won't see one of these self-lensing events. Likewise, they're very good at constraining the mass of the compact object. How big of a increase in brightness we see is tied directly to the mass of in this case, the black hole. And it also depends on the radius of the star. If you have a smaller star, we'll see a larger increase in brightness. And if we have a bigger star, we will see a smaller decrease or smaller increase in brightness. It's like holding a magnifying glass up to the Empire State Building. So wouldn't see much of a change. Now, we've seen this effect in 5 systems so far, so they're very rare. And currently, of the stellar mass cases, we do not have any examples of a black hole doing this, or a neutron star. All 5 have been white dwarf stars that have gravitationally lensed a companion that is a lot like our sun, actually, in terms of mass and radius. So what do these look like in the light curve? One good example here, this is real data from the Kepler Space Telescope. And what you'll notice is that there are 3 increases in brightness that happen periodically throughout this time span. They are separated exactly by the same amount of time between each. It's like 418 days or something like that. Just like the exoplanet transits, they are periodic. If you see more than one of them, you will instantly know the orbital period of the system as well, which is very useful. So if I zoom in on one of these, we can have a clear picture of what they look like. So towards the left over here, the lensing event hasn't begun, and we can see that that star is relatively around its average brightness, that relative flux value of 1. Eventually, the white dwarf star will slowly start passing in front of it, in front of its companion, and we'll see that increase in brightness. In this case, it kind of levels off just a little bit, and then as the lensing event ends, it returns to its original brightness. Now, the shape of the self-lensing pulse depends on a few things, but one very important parameter is what we call stellar limb darkening. And I have a very cool picture here that showcases this. I actually took this picture on the day of the total solar eclipse earlier this year. This was when it was the partial solar eclipse. The big black disk here is the moon, and the orange disk is that of our sun. And what you'll notice, if you look at the edges of the sun, it's actually dimmer than towards the center. This is an optical effect where we get these dimmer edges in a brighter center. And this is how it affects the lensing pulse shape. So gamma is our limb darkening coefficient. Gamma equals 0 means that there is no limb darkening, so it's basically all one color throughout the entire disk. And as we increase gamma, we're increasing the amount of limb darkening there is. For gamma equals 0, we get kind of like a box shape. But as we increase gamma, 2 things become apparent. The height of the self-lensing pulse will increase, and the shape of the self-lensing pulse is a little bit more rounded. So by seeing if there is this rounded shape in a self-lensing pulse, you can get a sense as to what the limb darkening is. Now, let's say I have an example where I have a system that has all 3 effects present at the same time. Well, its light curve would look something like this. So each effect is denoted by these dashed lines here, and the total light curve that we would see is the solid purple line. This is for a black hole that has a sunlight companion, a 10 solar mass black hole with a sunlight companion, in an orbital period of just 3 days. And if we saw this when we go out and looking for light curve data, this would be very apparent. There would be very little else that this could be if all 3 effects were present. But all 3 effects don't need to be present. You don't necessarily need a self-lensing pulse. You can have just the Doppler boosting and the ellipsoidal variations, or you could have Doppler boosting and self-lensing, or just self-lensing. It doesn't really matter. What SMILE can do is it can fit to any one of those effects, regardless if all 3 are in place. We have versions of SMILE that remove each effect if you don't want to fit to all 3, if it's clear that not all 3 are there. Now, when we started with SMILE, it was originally written in Mathematica, which is a program that I was trained to use in undergrad. It's very useful. It's very exciting. But Mathematica has a couple problems with it. The first, it is not free. It is decidedly not free. It's very expensive. And we want SMILE to be very widely usable. We don't want it hidden behind a paywall that we can't control. So Mathematica wasn't necessarily the best place to house it if we want to give this to as many people as possible. Likewise, the lensing part of the model requires a numerical integral. It cannot be solved exactly. There's no analytical solution for it. And unfortunately, Mathematica can be quite slow when doing numerical integration, at least compared to analytical. Much slower than other programming languages like Python or C. Yes, I know it's not technically a programming language. You always correct me when I say that, but it is what it is. So we decided that we were going to translate the whole model over from Mathematica, which was kind of our test bed, over into Python. It's free. It's widely accessible. A lot of people use it nowadays, and it can solve numerical integrals much, much faster. Well, here's the question: how much faster? So I have a fun example for you. So the current version of Smile is Smile 2.4. It's written in Python, largely worked on by myself and an undergraduate student, Liam Neely, who was very influential in the translation from the Mathematica version over to Python. I got to give him props for that. I really appreciate his help over the year and a half he worked with me. Let's say that if I have a particular data set, Smile 2.4, our latest and greatest version, takes 8 hours to fit to that data set. Now, it can take much less than that. It's tied directly to how many data points we have. So the more data points we have, the longer it'll take to fit. It uses a Markov chain Monte Carlo ensemble sampler for the fitting algorithm. It's a very popular Python package called MC, or sometimes called the MC hammer. Now, let's say I want to fit to the same data set with our original Smile 1.0 version in Mathematica. Let's say by some miracle, I'm able to do the exact same fitting algorithm in Mathematica. So the only thing that's different is just the numerical integration. How long would it take? Well, it would take roughly 16 years to fit to that 8-hour long data set. And that's assuming that the fitting is done in parallel. So it's using all the cores and threads on my machine, just like it is for Smile 2.4. Now, for those who don't know, I'm not particularly good at parallelizing Mathematica functions all too well. I always had a little bit of trouble with that. So let's make the assumption that I would have solved this in series, so single-threaded. It would have taken 147 years to solve. I was hoping to earn my PhD this century, so I'm very happy that we ended up making the translation over into Python. So how do we know that Smile is doing its job correctly? How do we know it's returning the correct parameter estimates? Well, one thing we can do is we can fit it to synthetic data. So this is data that we create using the model. We have the model, we plug in certain parameters, like certain values for the mass of the compact object, star, etc. We add a little bit of noise, we add some error bars, and we get something that looks like this. Theoretically, since we know what the correct values are, if we return those, we know our fitting algorithm is doing a good job. Now, a couple of things you'll notice in this synthetic light curve, there's this Z shape going on. This is a combination of Doppler boosting and ellipsoidal variations, so it's both running at the same time. And you'll also notice that we have this pulse in the top left here. This is our self-lensing pulse, and you will notice that there are more data points here. We actually have good reason for that, and we recommend people who use Smile, if you have a light curve like this, to have a higher sampled pulse. If you have more data points on the pulse, what you're doing, if you have a self-lensing pulse in general, you immediately know what the inclination has to be. It has to be very close to edge on. If you don't have a self-lensing pulse, technically speaking, you can have any sort of inclination value up to a point, right? I mean, even if you have inclination I equals 20 degrees, there'll still be Doppler boosting, there'll still be variations, there'll just be less of it. So if you have more data points on the pulse itself, Smile will fit harder to that point in the light curve, which is what we want. We want it to focus on the lensing pulse first, and then on the rest of the light curve second. So how do we do? So this is our model fit to the data. The orange thick line represents our 95% confidence interval. So we're 95% confident the correct answer is somewhere in there. And then the dark gray line is our 50th percentile estimate. So that's the one that we cite. And we zoomed in on the pulse here just so we can see how it fits at that point specifically. Now looking at our parameter estimates, the right column here is our true values, and the left column is what Smile returned. And what we found in this case is that Smile successfully returned every true value. Every true value was within the error bars of our Smile estimate. So this was a good test that our fitting algorithm was in fact working, and that we could at least trust it to get the correct values. Now, stepping back to our original self-lensing pulse that we had earlier, what you possibly noticed is that there is no Doppler boosting and there is no ellipsoidal variations in this light curve. It was purely self-lensing. The white dwarf was very far away, and those other two effects decrease in strength the farther the two are apart. So we got a self-lensing pulse, and what we can do to that is, if you want to fit to it and you don't want to include Doppler boosting, ellipsoidal variations, like I said, there are versions of Smile that can do just self-lensing. But self-lensing on its own doesn't cover all the parameters we want. It's very hard to estimate orbital eccentricity, argument of paraapsis based solely on this event here. But what we can do is we can turn to another data set that we can fit simultaneously to, which would give us those other parameters back. And that would be radial velocity measurements. This is through spectroscopic observation. So we're not going out and collecting light curve data. We're not seeing how bright the star is. We're collecting its spectra, taking the light from the star, we're breaking it up into its component wavelengths. And what will happen is that we'll see that often these lines, these are, in this case, absorption lines. And if you look at a star long enough, what you may notice is that these lines are moving back and forth. This will happen if the star is in orbit around something, if it is actually moving towards and away from us. This is very much the effect that drives Doppler boosting, but it is a different data set that we're looking at. We're not looking at light curves, we're looking at spectroscopy. So what I can do is I can take spectroscopic data from one of these self-lensing systems, and I can joint fit it simultaneously with the light curve itself. So I have the light curve on the left. So that was a self-lensing pulse from one of the real-world self-lensing systems. And then I have radial velocity data for that same system. And these models are tied together. We're using the same orbital motion code that solves the orbit for radial velocity as does it for the self-lensing pulse. So it's all tied together. It's not two models working independently. So this system we did not find. This was one of the first known systems. Likewise, there was a study that did their own parameter estimates for it. So we wanted to compare our model, our way of doing things, which is a little bit different from theirs, to their results, just to see if we agree with established literature. So we have our estimates right here in the left column, and we have the estimates from the original study in the right column. And what we found is, in general, we were markedly similar to what they found. There were only two parameters, as far as I remember, that we found to be statistically different than that of their estimates. The first was argument of paraapsis, and the reason for that was actually pretty straightforward. When they did this original study, they only had half of the radial velocity data, whereas we have the entire orbit. They ended up going back and writing another paper where they got the full orbit, which is the exact same data we use. They only fit to the radial velocity in that they didn't bother doing the light curve. But when they did that, they found an argument of paraapsis of about 4. So all of a sudden we are back in agreement with one another. The other thing other parameter that was found to be a little different was that of orbital inclination. We didn't really overlap there, but both of our results ended up saying that this is, again, a practically edge-on system. And part of the difference we may have observed likely comes from that argument of paraapsis difference to begin with. So in general, we were agreeing pretty well with them. Now, changing gears real quick, I want to direct you back to this kind of image we have here. So we have a black hole, and it is going to gravitationally lens its star. It's a very cool image. It's made in Space Engine. Very proud of it, and it's a very good visual aid as to what this effect looks like. However, it's a little bit misleading because in order to capture this, the camera, the thing that's making the simulation, is not only within the binary system, which we are definitely not when viewing it from Earth, it's also very close to the black hole. And this has a few effects. The first of all is that the black hole looks much larger relative to the size of its star than it would all the way here on Earth. Likewise, the Einstein radius is a bit smaller. So the black hole looks much bigger relative to the star and the Einstein radius itself is smaller. Now, I just want to give you guys a good visual aid as to what it would more or less look like from the Earth. We had an infinitely powerful telescope, and whether or not the size of the black hole will make any difference on the light curve. So looking at the Einstein radius, let's say I set up a scenario where I have a binary system that has a black hole, say it's a 3 solar mass black hole, and a sun-like star. It's a circular orbit. They are always half an astronomical unit away, so half the distance from the Earth to the sun. Let's say its Einstein radius is approximately this large. This is our kind of our baseline for everything else we'll do. How large would the black hole be relative to its Einstein radius? I'll put it in right now. Now, you may have thought that I didn't put anything there, but if you look really closely, you'll see the smallest possible dot I could put in PowerPoint. That actually may be even slightly bigger than the black hole would be. I think PowerPoint does have a limited size capability. It is very, very small. And this is the same for neutron stars as well. They do not take up a significant fraction of the Einstein radius. It's a good approximation to say that they're basically not there. We call these point lenses, more or less point mass lenses. But white dwarfs are much bigger. White dwarfs are much bigger than that of black holes or neutron stars. They can be roughly the size of the Earth. Black holes and neutron stars can be the size of like Lowell, as an example, at least the stellar mass cases. So let's say I change the scenario. Let's take our black hole, get rid of it, and put it in a white dwarf. Let's say it has 0.3 solar masses, so it's 10 times less massive than the black hole we just had. And let's put it at the same distance away. So the only thing that's going to depend, or that the Einstein radius size will depend on, is the mass of the compact object. Well, that white dwarf's Einstein radius would be this large. So it's smaller, but it's not like hysterically smaller or anything like that. It's still visible. But here's my question is, how big is the actual white dwarf relative to its Einstein radius? Well, in this case, it actually ends up being that big, just a little bit bigger than its Einstein radius. That's a little problematic all of a sudden. All of a sudden, it is now a significant fraction of the Einstein radius, and that is going to affect our lensing pulse. Now, you may be tempted to say that, well, there's just going to be no lensing now. But no, the Einstein radius is not where lensing ends. So just to give a slightly different example to visualize this, let's say I have this Einstein radius here, and it's going to lens a star that is a little bit smaller than it. So it's a little bit smaller than the Einstein radius. Well, its image, when the Einstein radius passes directly in front of the star, will look something like this. It will be a disk, some kind of annulus with that hole in the middle. And what you'll notice is that this image has some kind of thickness to it, right? It's not going to be infinitely thin. It's going to have some inner and outer boundary like so. And in the case that we just had, if the white dwarf is a little bit larger than the Einstein radius, it doesn't block the full image. We still get lensing, albeit it's going to be less lensing than before because that secondary image, the inner part here, is going to be completely covered and some of the outer part will be covered as well. So what is this going to look like on an actual light curve? So I got this space engine video kind of to give us that visual representation. And if you pay attention to the top right of your screen, we're going to plot what that light curve looks like as a function of time. Okay, so I hit play. The white dwarf is going to come in. It is a little bit larger than its Einstein radius in this case. We'll see lensing begin. And then very quickly, it ends up going back down before shooting up, getting a normal shape, and then it repeats. Now I'll let it play one more time, and I'll pause it directly when that decrease happens. Right here, close enough. So a couple of things you may not have noticed right away. There's no secondary image. There is a secondary image, but it is completely covered by the white dwarf surface. So already we're actually starting with less lensing than normal, because normally we would see that secondary image. Now we see that the lensing effect starts, it's going up very quickly. And then at this point, it shoots down. And the reason for that is now the primary image, which is basically just this star here, part of the primary image started to be covered, but not that much of it. So even though it goes down and we get that drop in brightness, it then ends up going back up. I hit play, it should still go. Now, it's over. It goes back up and we get just the normal self-lensing pulse, albeit it is a smaller height than it would have been if there was no finite lens effects. That's what these are called. Now, what happens if I make the white dwarf a bit bigger? Well, I'll have that in this example here. So same thing, light curve is going to be plotted in the top right. And white dwarf is going to come in. It's a little bit larger than last time. We see lensing begin, but all of a sudden it shoots down. There's a decrease in brightness instead. There will be a point where you'll have more occultation. So the physical size of the white dwarf will be blocking more light from the star than lensing will be able to increase. So we saw lensing start first because it happens kind of before the white dwarf passes over. But eventually the white dwarf will be large enough that it's going to be blocking too much of the light. So we get a decrease in brightness. There's still some lensing though, and you can see it fight back here. It goes back up for a brief period of time. So the effect of occultation is reduced by the self-lensing pulse. It's still fighting against it, but there is more occultation than there is lensing in this case. If you made it even bigger, eventually you'll lose the lensing effect completely. So changing gears yet again, I want to talk to you about the SMILE project, a project near and dear to my heart regarding the search for self-lensing binaries. So it's our own search for more. SMILE is only useful if we have more binary systems that we can fit it to. So we got to go out and find more. This is a citizen scientist project. You do not have to be a professional scientist to join in on the fun. Anyone can. It uses light curve data from a combination of the TESS and Kepler space telescopes. Kepler is specifically taking stars from the Kepler object of interest list, and TESS is coming from the candidate target list. We've filtered that list to over 24,000 targets in our initial search that meet these three criteria. The first is that the declination of the star must be between 45 and 90 degrees. That is oddly specific, but we'll talk about that reasoning in just a minute. The TESS magnitude, which is just how bright it is from TESS's perspective, must be between 8 and 11 TESS mag. For those who don't know, a lower number means it is a brighter star. And the last thing is that the estimated stellar radius of the star in the mass database must be between 0.1 and 1.2 solar radii. The reason for that is we want to focus on stars that are either similar in size to that of our sun or a bit smaller than that. We don't want the really big red giant stars that are 20 something times the size of our sun, because again, the larger the star you have, typically speaking, the smaller the lensing pulse will end up being. So we want to kind of maximize our chances for seeing one of these. Very important, users need little to no coding experience to search. It's actually pretty simple. We have 5 undergraduate students who have joined this project this summer with various levels of coding experience, all the way from being relatively proficient programmers to having never done anything in Python before. Took about 45 minutes to set them up when they didn't have Python with the Python packages they needed and the codes that will allow them to search through the data. It's very simple. Now, in my own search, so even before this this list was created, I went out and I went looking for some things, and I found this, which was very exciting originally. I was very curious what could possibly be happening. It was a symmetric increase in brightness and then followed by a decrease, and it looked a lot like what a self-lensing pulse looks like. But there were some weird things going on. I noticed that the height was quite a bit larger than any self-lensing pulse we have, and that's not necessarily impossible. And you can have self-lensing pulses that are much higher than that. But I also noticed that the time scale was quite a bit shorter than any of the self-lensing pulses we observed. So there were some fishy things going on. And I had enough foresight, thanks to Silas's teaching, that if anything weird's going on, you may as well check the actual images, see if anything weird happened. So you're able to do that with Python. So this is more or less what TESS is seeing. This is a target pixel file image. The star that we're looking at is directly in the middle. And all these white boxes around it are what are called our aperture mask. This is more or less counting all of the photons in this image. It's counting all the photons that are coming from the star. So that's telling us how bright it is as a function of time, more or less. And I can make a movie out of this just to see if anything weird's happening. But I mean, like, what could we see? So that was an asteroid. I was not planning on this, and I did not know that this could happen. So what ends up happening is an asteroid came in, it's reflecting light off the sun, so it has its own brightness associated with it. It passes into our aperture mask. It does, like the aperture mask doesn't recognize that another in it, it's just counting photons. So when that asteroid with its own photons, it thinks that star just got brighter, and the shape of that crossing event ends up looking a lot like a self-lensing. Fit our self-lensing model to it. It's pretty well, actually. That's a little problematic if you want to automate the search for self-lensing pulses. If you come up with some machine learning algorithm that's going to constantly search through test data, it will more than likely run through into a lot of these, and it might not be able to tell the difference. Theoretically, we wanted to fit to these because we wanted to see what kind of parameter estimates they would end up returning, if they ended up making sense or if they were kind of weird. And the answer was they were kind of weird. They still are possible, but they were characterized by higher mass compact objects. So most of them were black holes, at least like 10 solar masses. and higher impact parameters. So they weren't perfectly edge on. In this case, the center of the lens wasn't even passing over the star, which we haven't seen with a self-lensing pulse yet. So there may be a way to actually train a machine learning algorithm to recognize or at least flag these as possible asteroid crossing events. If you're searching yourself with the SMILE project, the easy way to tell if there's an asteroid is that there is a cell that you can run that will show you the images and you can see if anything passes in front. We have found quite a bit of these, but we've been finding less. And the reason for that is our choice of declination for our list. We decided to aim above the plane of the solar system, where the majority of asteroids are found, not all of them, but the majority. And in doing so, we've been finding about 4 or 5 times less asteroids in our search. So we've reduced the number that we keep running into by a factor of 4 or 5. So overall, a good thing. Now, Silas remembers this one because I frantically emailed him after seeing this because this was very exciting. We had 3 repeated increases in brightness that were symmetric in shape. And this kind of up and down motion that almost looked like either Doppler boosting or ellipsoidal variations. This actually looked very much like one of our simulated synthetic data sets that we had. So I got very excited when I saw this, and I was very concerned that maybe we had something. But there were a few things in this light curve that were questionable that made me think that maybe it wasn't a self-lensing event. But there was no evidence of asteroids in the images. And obviously it happens 3 times in a 27-day period. Sorry, aren't gonna have an asteroid come back in that time scale. But what we decided to do was check the background flux. So we have our aperture mask, and that's counting all the photons in that space, but there's going to be a brightness associated with the rest of the image. So stuff's happening in the background, and you can check to see if anything weird's happening in the background. And in doing so, this is what it looked like. And what you'll notice that there are 3 dips that correspond to the exact same times in which our pulses occur. What's happening is that there are these very large dips in the background. When you get test data, it has to go through some kind of pipeline to reduce systematic noise, spacecraft jitter, other background effects that may be present. And when you have these very large dips in the background, what can happen is that the pipeline will overcorrect and subtract these out, which comes out as increases in brightness in our light curve. So if I looked at the actual image, we were very curious where in the image these dips were coming from. Our star that we were focused on was here, denoted with the crosshairs. And we were able to narrow down where these dips in brightness were coming from to this general area. There are 3 main stars here that are pretty similar in brightness, and we couldn't actually figure out which star it was coming from. The reason this test doesn't have necessarily the best angular resolution, and they're on the dimmer side, so it's harder to get higher quality data from, higher signal to noise. But so what we did is we made an aperture mask around those pixels specifically. And this is what the light curve ended up being. And you can see 3 absolutely massive dips in brightness. So this is almost certainly coming from some kind of eclipsing binary system. So it's 2 stars that are passing in front of one another, which is decreasing the overall brightness that we see. And those are interesting, and we would like to figure out exactly which star is the eclipsing binary. But there's something a little bit more interesting in this light curve. If you look closely, you'll see these smaller, more frequent repeated dips in brightness. We're not 100% sure, but based on the depth of these decreases, these very well likely could be an exoplanet transit. To the best of our knowledge, there are no known exoplanets in this region. We don't necessarily know which star this is coming from. It may not even be in the same system as these large eclipsing binary dips. This is kind of perhaps a Frankenstein's monster of all 3 stars' light curves because of the contamination. So this is something we're actively looking into, but there is a chance that we found a new exoplanet by searching for self-lensing pulses. Part of why we do it. Now, in our search for self-lensing pulses, currently, we have not found any new confirmed self-lensing systems. But what we decided to do was take a look at the 5 that are known, or at least 4 of them. Because what TESS does is it observes a very large swath of sky, which we call a sector. A lot of stars are viewed at one sector, and these sectors last about 27 days, before TESS moves on to another swath, with the express purpose of imaging as much of the sky as possible, as many stars as possible, in hopes of finding more exoplanet transits. A side effect is perhaps more self-lensing pulses as well. But there's a problem with this. So, like I said, it observes every 27 days before moving on to another sector. But four of the five self-lensing systems have orbital periods greater than 400 days. That's a little bit of a problem because if TESS is viewing a sector for 27 days, you actually have a very low probability that it's aimed at your self-lensing system at the correct time. These self-lensing pulses, the ones that we have so far, only last about a day or two. So it's a day or two out of 400. One of them has an orbital period of 700 days. So you got to get lucky. And for those four main ones, 3 of them, we did not get lucky. TESS did not observe those at the correct time. But for one of them, we got a little bit extra lucky because not only did it observe it once during one of the self-lensing pulses, it actually observed it twice. So knowing where those pulses were supposed to occur, because we knew what the orbital period of that system was, we were able to take those data points and phase fold over them so we could combine them into one better sampled self-lensing pulse. And these were the first self-lensing pulses that were reported as observed by the TESS Space Telescope. So we decided to fit our model to them and compare to the original Kepler pulses of the same star. So these are our fits. The top is our TESS, and the bottom is our Kepler. The plots on the right are the radial velocity curves from this star. They are both from the data sets are taken from the TRESS spectrograph in Arizona. So it's the same radial velocity data and different light curve data. And what you'll immediately notice is that the Kepler pulse is significantly more well-defined. It has a very defined shape to it, and you'll notice its confidence interval is much smaller because in general it is more confident. The error bars are also smaller as well. Now, for the self-lensing pulse with TESS, you'll see that the confidence interval is larger. The shape is in general much less defined, and the error bars are much larger. TESS is a little bit less sensitive than Kepler is. It has less signal to noise. And this star is basically pushing the boundary of what we would be able to see. This is a 12 TESS magnitude star, and we're using that kind of as our baseline when we made the decision to go from 8 to 11 in our own search. Don't get me wrong, when we phase fold here, you can see that there is an increase in brightness. These increases did correspond exactly in time to when we expected these self-lensing pulses to occur. But I did say, even in the paper, that if we didn't know that this was a self-lensing system, when we got the data and we had the raw light curve, I would not have recognized that this was a self-lensing pulse. It really took a lot of binning and the phase folding to bring it out like this. So that's why we've set that limit on the brightness of the star being around 11 TESS mag. Now, question: why do we search? Well, obviously we want to find more self-lensing systems. They are rare. We only have 5 currently, but we expect there to be significantly more of them, and currently TESS is considered to be the best instrument for finding them. Likewise, we want to find Doppler boosting systems. We want to find ellipsoidal variables as well. There are more of those to be found too. But part of why we search is because we actually don't know what we're going to find. And every now and then we run into some fun things that were unexpected. And part of what makes science is looking for the unexpected. So this was something that one of our undergrads found relatively recently. That was pretty cool. We're not 100% sure yet what this is, but we're pretty confident based on the shape. It is some kind of comet. You can see the nucleus here, and you can see what appears to be a tail structure as well. If it is a comet, we don't know exactly which comet it is, but based on the timing, there is a chance that it was actually Comet Neowise from 2020. This happened at the same time, but I have to go back and check to see if TESS was viewed at that point in sky at the same time. It might not have been, but this is relatively new, so I haven't been able to look. Likewise, I want you to pay attention to this star here that's circled with the red disc. I'll play it again. You can actually see it's flashing. This was unexpected too, and we ended up making a light curve of this. This is an RR Lyrae variable star, so a lot like a Cepheid. Wasn't what we were looking for, but that doesn't mean you can't do some interesting projects on it. We collected that data, we checked the period of its pulsations, we phase folded. It was a lot of fun. It's a good project for Bailey to do it as well. We find random things like this that are cool, but every now and then we find something that kind of looks like what we're looking for. So this is one of our candidate self-lensing pulses. It's not confirmed. We don't know for a fact if it is. It only happened once. I think this system was actually only observed twice by test, so we don't have a lot of data for this one. But what we see over on the left is this symmetric increase in brightness, a very similar relative flux increase to the known self-lensing systems. When we threw it into our model, we obviously don't have radial velocity on this, so it had very large error bars, but the mass estimate was white dwarf, similar to the ones that have been found so far. It's not guaranteed. There are other things that this could potentially be, but we know from what we could tell, it's not an asteroid. There was nothing in the background. So this is a candidate. And it's not our only one. We have these other two here and maybe a couple other more. Now, all of these only had one lensing pulse or one lensing shape, not necessarily lensing pulse. So they're not confirmed. If we saw more than one, it would be a much higher impact candidate. But what we're going to do, and what we're already doing for the first one, is we are going to collect radial velocity data. So we're already using the TRESS spectrograph in Arizona, thanks to Dave Latham at the CFA, who was very happy to look at our targets. And we'll see. We actually won't get that data for another month or so. It may end up coming out that this is not a self-lensing pulse, but that's why we got to look. So the question I have with you, or for you, is with all of this potential for discovery, whether it be self-lensing pulses or Doppler boosting events or all these other fun things that we find in looking potential exoplanets, and how easy it is to run all of this is why aren't you smiling? Okay, you can be smiling very soon. And it's a very quick setup. If anyone wants to be smiling shortly after this, feel free to let me know. Now, to kind of wrap up everything, I want to talk a little bit about the future. It's always a good thing to start. So SMILE 3.0 is currently under development. Very excited by this. One of the main points of SMILE 3.0 that we want to happen, faster computation times. Faster is always better. We are definitely better than taking 147 years for one data set. That doesn't mean we can't code a little bit better to make it a bit faster. Obviously, as technology gets faster and faster, SMILE itself will get faster, but that doesn't mean we can't figure out ways to fix that now. Another thing is we want to be able to predict when in the orbit the lensing pulse will occur. Technically speaking, if you know the argumentative paraapsis of the system, you will be able to figure out exactly when in the orbit the alignment is perfect for the lensing pulse. Right now, we have that as a free parameter called T0, which is the closest time of approach. Closest approach, yeah. And that's fine, but if we can get rid of one more free parameter, we may as well. It's up to us. But that will be an optional feature, but I am still working on that. And I have it more or less figured out, but just got to do some more checking or testing. As for the SMILE project, all codes are to be made publicly available with startup tutorials. Right now, whenever anyone wants to start, they set up a Zoom call with me, and then we get them started with the packages. But it's actually really not that many steps, so we'd like to just have a kind of a website where people can do this. And all single event pulses that we found, the ones that we consider to be interesting candidates, we want to follow up with spectroscopic observations. Now begins what I call the thank you-a-thon. This research was funded by the NASA Finest grant. So thank you very much to them for funding us in my final year here. And it was partly funded over the course of the past few years by the Massachusetts Space Grant Consortium. I want to give a very special thanks to all the members of the SMILE team. We have our theory team, which is more or less just our research group. I always got to give a big thank you to Liam Neely, who was very influential in the development of the Python version. He and I worked together and made SMILE as fast as we could possibly make it at the time. Got to thank you to the Observer team. Those are our 5 undergrads that recently joined. They're doing a great job, and I'm proud of them, and I want them to keep looking. Got to thank our committee members. Silas, you're very special. You get mentioned twice, actually, so you're extra thank you. But these three were very helpful throughout my time here at Lowell, and I really appreciate all the advice they've given me. Collaborators, my undergrad advisor, Alessandro Maserati, Andre Nicholas, Kento, and David were all very helpful in getting me various kinds of data. Kento and Dave got me the radial velocity data from the self-lensing systems. All you members of Locus that are here, thank you very much. You've been very helpful throughout my time, and you've always been able to help answer some of my more interesting questions with how to do things. So I appreciate it. And I got to give a very special thanks to Professor David Simon from Stonehill. Shortly after my conversation with Silas, that led to me thinking about self-lensing systems for the first time. I hadn't heard of them. And I went to Professor Simon and asked if this was possible in his opinion. He was like, yeah, probably. And it was that affirmation that led me down this crazy road in the end. So I got to appreciate him telling me to look into it more. And of course, I got to give a very special thank you to my wife, Jennifer Sorabella, who has not only been extraordinarily supportive throughout this entire time, but who has also edited quite a bit of our grammar and our research papers over the past few years. So the quality of our English has greatly improved thanks to her. And of course, after years of watching PBS, I've always learned that you're supposed to thank viewers like you. So that's it. So if anyone has any thoughts, comments, or statements of outrage, now would be the time to ask.